Astrophysicists have discovered a black hole that has been emitting particle beams in opposite directions for millions of years. Recently, it has shifted to point one of these jets directly at us. However, there is no danger from this phenomenon. It is an intriguing event that has never been observed before. Quasars are the most extreme phenomenon in the universe after the Big Bang. They are produced by gigantic black holes at the centers of galaxies, which shred matter and emit a tremendous amount of energy. Quasars belong to a larger category of objects known as active galactic nuclei, AGN. AGN encompass various phenomena associated with supermassive black holes accreting matter. This includes Seyfert galaxies, where smaller black holes and spiral galaxies consume matter, and radio galaxies, which emit jets of material that produce radio light. Blazars are a subtype of AGN where the jets are directed towards us. These different types of AGN are related based on parameters such as the size of the black hole, its feeding activity, the formation of jets, and the orientation of the system. Understanding that these diverse objects are manifestations of the same phenomenon has provided clarity in their classification. However, there have been cases where AGNs transform from one type to another, which adds complexity to our understanding. And the weirdest example of this is when an entire AGN, gigantic black hole included, appears to have rotated on the sky to point straight at us. To see why this is so weird, let's take a look at what makes these different objects what they are. This is the basic picture of the active galactic nucleus. We have our supermassive black hole that can be anywhere from 1 million to several billion times the mass of the Sun. These things live in the cores of all decent-sized galaxies, but mostly they're not feeding so we can't see them. In some cases, though, we have the accretion disk, gas from the surrounding galaxy that for some reason has been driven into the core and is spiraling into the black hole. On its way in, friction between the different orbits heats the gas up until it glows and radiates light from infrared through to extreme ultraviolet and even X-rays right near the black hole. Surrounding the disk, we think there's a giant region of very dusty material, often called the dusty torus, that's fueling the disk. We also have wings-move material swirling around or being blasted out, which produce bright spikes of light that correspond to specific elements found in those winds. And sometimes those outflows are gathered up, collimated by magnetic fields. They're channeled into beams of matter that punch their way into the surrounding galaxy. Charged particles spiral in these magnetic fields, emitting synchrotron radiation. The energy of that radiation can be extremely bright, invisible, ultraviolet, or even X-rays and gamma rays by some more exotic processes close to the black hole. But the light from the jet has lower energy if produced further from the black hole. On the largest scales, when the jet has punched far into the surrounding galaxy, or even into the empty space beyond the galaxy, it shines as radio light. Exactly what we see when we look at one of these beasts depends on a lot. But one of the most important factors is orientation. In the classic quasar, the accretion disk is fully visible. Technically, quasars should also have a jet-producing radio emission. After all, the word quasar comes from quasi-stellar radio source, with the quasi-stellar part just meaning that it appears small, point-like to our telescopes. But there are also cases where you can't see the accretion disk at all. If the object is aligned sort of side-on, then the disk is obscured by the ring of material that surrounds in. Then all you see is the radio jets. These are radio galaxies, of which there are also different types. But the coolest are the double-lobe giant radio galaxies where you have thin jets of matter extending for up to millions of light years from the galaxy before blossoming out into gigantic radio plumes. When the jets of a galaxy are pointing along our line of sight, we observe unusual phenomena. The intense speed of the material in these jets, often close to the speed of light, causes a significant increase in brightness due to the effect of Einstein's special theory of relativity. This relativistic boosting can amplify the jet's brightness by a factor of 1,000 or more, resulting in what we call a blazar, an active galactic nucleus, AGN, with extreme synchrotron emission. Blazars also exhibit rapid flaring activity, as the jet is irregularly fed by the accretion disk, and the high velocity of the jet accelerates its bursts. In summary, Radio galaxies and blazars originate from the same physical object, with the only difference being the observation angle. We see radio galaxies from the side, while blazars are observed down the barrel of the jet. In the case of the newly discovered PPCJ 2333.92343, it appears that a radio galaxy has turned its barrel towards us, resulting in the blazer-like behavior observed. The recent study conducted by Lorena Hernandez Garcia and collaborators utilized observations across the electromagnetic spectrum, revealing that the jet in this object was pointing directly at us, or at least within a few degrees of our line of sight. This discovery is intriguing for astrophysicists, as it challenges our understanding of the relationship between jet orientation and the overall nature of AGNs. The shift in direction of the jet from the radial lobes to the blazer-like jet is likely due to the jet changing direction over time. The exact mechanism for launching these jets is not known, but it is plausible that powerful magnetic fields near the black hole pull up material from the accretion disk and channel it. One hypothesis is that rapidly rotating black holes with highly ordered magnetic fields produce powerful jets. To change the direction of the jet, the orientation of the entire supermassive black hole, or the axis it spins around, needs to change. This would require a significant amount of energy. One way this could happen is by changing the orientation of the accretion disk. Each time gas falls into the black hole and forms a disk, it may be at a different angle, potentially causing a change in the orientation of the jet. The first radial lobes could have been created in a previous event that spun up the black hole and produced jets on either side. The active galactic nucleus may have then become dormant before being reawakened by a new event. If galaxies merge, the angle of the merger affects how gas falls onto the central black hole, possibly changing its spin. A significant merger could result in two supermassive black holes merging and the spin direction of the final black hole depending on the combination of the original spins and the angle of the merger. It is possible that the observed jet direction is a result of both spinning up the black hole and the black hole merger. The dynamic nature of the universe is highlighted by observations like this, showing that the night sky is not static but constantly in motion. Additionally, this provides a new opportunity to study astrophysical jets, their connection to black holes, and the life cycles of active galactic nuclei. The Patreon shout-out is given to REC for their support, and a live stream is planned to answer comments and questions from the audience.